Name's James Weaver. I'm a developer advocate with Pivotal. I have the best job in the world. I get to play with Pivotal technologies, Java and Spring and Cloud Foundry and some others, and then I get to travel all over the world and speak about them to developers, which it's a dream job. So I tweet there. My blog is javafexpert.com, and there's my email address. This is one that I'm going to do with Dr. Johan Voss. Some of you may know him. We're going to do it at Java 1, as well as, come on in, Geertjan, as well as in Belgium, and at Devox in Belgium. He's not here today, and so you're gonna learn about ket notation if you haven't already. But what that represents is there's a superposition, a quantum superposition of myself and Johan, in which his phase is 80 degrees out of phase. I'm just saying he's not here, kind of thing. And about me, I've told you a little bit about me. I've written several Java books, beginning in '97, Inside Java, and then Java EE, Java FX, and most recent one was with Stephen Chin with Raspberry Pi and Java. And then I work for Pivotal. Pivotal, of course, we steward Spring, all the Springs, Spring Cloud, Spring, Spring Boot, Spring Data, all the Springs, as well as Pivotal Cloud Foundry. Cloud Foundry is a cloud platform that runs on top of all the major cloud platforms and plus on-prem. So developers just develop to one cloud, and as that cloud moves around, they don't have to worry about it because they're just doing CF pushes all day. Pivotal Labs, we kind of consult, engage with customers, bring them in, pair program with them, teach them great agile processes. And then we have a new kid on the block is, who remembers New Kids on the Block, by the way? Check the age of the audience. So, yeah, okay. The new kid on the block is PKS, which stands for, oddly enough, Pivotal Container Services. We flunked acronyms, I guess, but it's actually, the K is for Kubernetes, and so it's production grade Kubernetes. So anyway, a great company. We have great technologies, but the coolest thing about Pivotal in my mind is our principles and practices. So these two people work for Pivotal, so you know what I'm talking about. But there's actually 5 principles and practices. 2 of them that aren't shown here. One of them is, get home in time for dinner. They really care about their employees. But 3 of them here are just common sense, right? Do the right thing, do what works, and my personal favorite is be kind. All right. So, I consider myself a kind person. I don't, it's not really necessary for my company to tell me to be kind, but I do appreciate working for a company that one of their core principles is be kind to people, whether they're employees or coworkers or, customers or whatever. And especially in this environment, this day and age, we just need to be kind to each other, right? And so it's really refreshing to work for a company that, from the CEO down, the CEO is all about inclusion and being kind and just treating people the way you want to be treated. And so it's really, I don't know, is it a cool company to work for, Glenn and Roy?
Awesome.
Yeah. So, what's that?
That's not me sucking up either.
Yeah, you don't work for me, so. Do I work for you? I haven't seen my boss in ages, so, okay. So anyway, I would like to invite you to Spring One Platform. It's about all the Spring stuff. It's in San Francisco, December 4 through 7, and it'll be a wonderful time. And now, I can't believe you all came here to listen. You're Java developers, and you all came here to listen to a talk on quantum computing. I appreciate you coming. This is the first time I've given this talk. I'm not sure how it's going to go, but I do know one thing. What's going to really help is if you ask questions, because then that will help me kind of know what kind of things to drill down into, and also it'll help me for future talks, because then I'll know what the audience is thinking about, especially since you're all hardcore developers. It's really going to help me. So who knows what that thing is right there? Let me just gauge the audience's knowledge here. Who can tell me what that spherical thing is, what it's called or what it's for? This is awesome. Okay, that is called a block sphere, B-L-O-C-H, like Joshua Block, the Java guy, right? That does the Java puzzlers. That's called a block sphere. Who's heard of a qubit? Okay, more people have heard of qubits, yay. Okay, so you can represent the state of a qubit in a block sphere. And by the way, this presentation has lots of links in it. It has links to great videos and papers and things like that. And so it is really resource rich. And so I would actually recommend following along, or at least getting access to it later. So history seems to be repeating itself. Back in the dark ages, circa 1947, late 40s, early 50s, computer rooms were just filled with massive amounts of hardware. I have friends that, okay, I wasn't around in 1946, but I have older friends that who their job was to create core memory. I mean, we're talking about little iron rings and like rings and sew them together and whatever and make bits. And so and we're repeating ourselves again, but now it's qubits. That's the memory, is qubits. But we're talking about massive pieces of equipment, cooled for superconductivity in the case of the IBM Quantum Project, cooled down to almost absolute zero, because molecules act completely different when they're super cooled like this. And so lots of different companies are making quantum computers. There's, of course, IBM. There's Google, a company called Regetta. Microsoft is working on one. Others, but they all do use different technologies underlying. They're all like subatomic particles and whatever, leveraging the quantum physics and quantum mechanics of some type of underlying layer, but they all quantum computers make direct use of quantum mechanical phenomena such as superposition and entanglement to perform operations on data. So regardless of whether the underlying is like photons or electron states or trapped ions or whatever, regardless of that, they all use they're all making use of leveraging these quantum mechanical phenomena. Okay, so what's quantum computing good for? Why is it becoming popular now? Well, one is there's a guy named Peter Shor, actually in 1994, he created Shor's algorithm. And the idea there is that that the RSA code, to break an RSA code key, you need to be able to factor into primes a very, very large number. And so that task, could take, I don't know, thousands of years. I don't know how many it is, but it's what they call NP hard. Where's Kelly? Where's Kelly, the doctor? Yeah, NP hard. Is it NP hard? Okay. All right. It's a measure of complexity, which means but the ability to take prime factors and multiply them and come up with a key, that's easy. And so RSA its effectiveness is based upon the fact that factoring the prime numbers are hard, but once you know the prime numbers, it's easy to go the other way. So what Shor did, Peter Shor, was he came up with a quantum algorithm to factor very, very large numbers leveraging quantum mechanics, so leveraging what I'll show you in a few minutes here. And so he recently did a paper that's a little bit easier to digest. It's in 1997 on the bottom there, and he was quoted in 2013, as saying, because they were asking him, well, is Shor's algorithm going to bring down civilization anytime soon, right? Because it's breaking all of our codes. And he said, if you start factoring 10-digit numbers, then it's going to start getting scary. So actually, I think that's James Gosling. Isn't that James Gosling? Has anybody seen those two guys in the same place? So I think it might be. Okay, questions so far? I would like a question from the audience. Or am I telling you exactly what you want to hear? Everything's good? You're all good? Okay. All right. So then the next year, a person by the name of, is it Love Grover? He's from India. And he created this thing called Grover's algorithm. And it has to do with being able to search unsorted data. And I like his quote. He said, programming a quantum computer is particularly interesting since there are multiple things happening in the same hardware simultaneously. One needs to think both like a theoretical physicist and a computer scientist. Okay, so because you have to know kind of both disciplines, and he would know, right? Because back in '95, he created just kind of a groundbreaking algorithm for the way that he characterizes it for finding a needle in a haystack. So it's unsorted data, but yet finding a particular key in that data or a record in that data. And then, so that's two of the uses, right? One is, factoring large prime numbers to break RSA. Another one is searching unstructured data. And one that kind of maybe the best fit is going to be probably simulating nature. I mean, what better to use to simulate nature than a computer whose underlying, underpinnings are nature itself, right? It's quantum mechanical. It's running on top of electrons and things, for example, doing simulations with chemicals or like chemical reactions, you need to be able to track the state of, hundreds, thousands, whatever of subatomic particles and different combinations or whatever, and you just run out of space in the computer, in a classical computer. But with quantum computing, because nature is your backing store, you don't easily run out of space. Now there are some gotchas, but anyway, this gentleman by the name of, who's heard of Richard Feynman? Okay, good. So just a famous physicist, really cool guy, and he was paid homage on Big Bang Theory when Sheldon was playing the bongos, because Richard Feynman used to like to play bongos, and so he's one of the founders of quantum physics. So really recently in Nature, which is a leading scientific journal. Yes, Matt. Matt, right?
Yeah. Okay. Do you think we'll need the simpler quantum mechanics of, say, entanglement to simulate the more complex ones like tunneling?
Okay, so the question is, will we need things like entanglement, right? So that's a quantum mechanic. That's something that just comes out of the box with quantum mechanics. The entanglement is a thing, right? Well, we need that for leverage that for things like you're saying tunneling or whatever. And so my answer is that yes, like one of the things that characterizes quantum mechanics is entanglement. So it's a core feature in any kind of sophisticated thing that you're going to do in quantum computing. So Nature is the kind of the leading scientific journal on, across the spectrum of science, or at least is a leading one. And in a 14 September issue, it talked about being able to use quantum computing to solve chemical structural problems. And so you can go to that particular link and read about that. Also, another big thing with quantum computing lately is this idea of being able to, it's not that new of an idea, but the distances are getting greater. It's called quantum key distribution, where if you can send a quantum key, kind of qubits, to some remote, somebody that you want to send you information, then you can send it in such a way because of quantum computing and quantum mechanics, you can send it in such a way that it's guaranteed that it can't be intercepted. If someone tries to intercept it, then the state of that qubit or pair of qubits or whatever collapses, and so nobody can read it. So it can't get compromised. If it does get compromised, then you know it because it's ruined. It's entangled, so if you compromise this one, then the other one is compromised, is then collapses. So what you can do then in these two articles, you can set what they've done in China, and both of these were Chinese researchers and companies that are into quantum key distribution, and then also quantum cryptography and quantum teleportation, which is just the ability to quote unquote teleport qubits from one place to another. They're actually doing that from ground to satellite, so shooting photons out into space and hitting a satellite, and then like entangling it first, shooting it out there, and then they observe this one, and whatever state this one is in, that's the state the other one is in. Spooky actions at a distance, as Einstein called it.
Is that for processing or just communication?
Okay, so the question is that for processing or communication? So there's several ways that these technologies can be leveraged. So one way is with quantum key distribution. If you can be guaranteed to send a key and guarantee that it's not going to be compromised because of quantum properties, then you can send the key, and it could be an RSA key, it could be whatever, and then you could then communicate classically, but you've used quantum mechanics, quantum computing then to actually distribute the key. So that's QKD, quantum key distribution. But then you could also, as we get more better communication, and that's one of the reasons for these tests, with the satellite communication, then you can start actually not only distributing the key, but actually then doing communication. And so this quantum teleportation is the idea where you've got some quantum state here, and then you've got maybe in the satellite, and then you've got an entangled qubit down here, and you can then send the state from here to there, kind of teleport the qubit from one place to the other. So it all sounds kind of spooky, but let's go to the basics. So those are some of the promises of quantum computing. So I'll just take you back to the basics. You're all developers. You all know what bits are. So that's where we'll start. So we have classical bits, 0 and 1. And then we have qubits. And by the way, there's a nice article down there that I lifted this drawing from. Qubits have 0 and 1. There's a block sphere, by the way, you remember that. And in a block sphere, the down state, the South Pole down there is actually the one state. That's the on kind of thing. And then the 0 state is the up state. And then you have, in 3 dimensions, all over the surface of that sphere, and only on the surface of the sphere, then you have an infinite number of states that a qubit can be in. And you've all heard of superpositions, right? And some people think in terms of that. They say, well, it's one or 0 or both or whatever, and it's kind of more correctly kind of a superposition of them. If you're familiar with just really like algebra, where you have like coefficients, and you have like linear combinations of different like variables, and then scalars that you're multiplying the variables by. So 2x plus 3y plus 4z. Well, you could think of that as a superposition, really. And so it's really just kind of a linear combination. And what makes it a superposition is that the qubit doesn't make up its mind. It can be in all these states kind of at once, and it doesn't really make up its mind which state it's in until it's observed or measured. And I don't mean some human has looked at it. It doesn't take a human, but it's measured in some way, right? So a photon detector has detected it, or whatever. And as I'll show you here, maybe a polarizing filter has detected it. So at that point, at the point that it's measured, then it collapses into either 0 or 1. Okay? Questions? Yes?
The way I kind of think about it is, like, growing up, we used to have the classic kind of solar system model of atoms, electrons, protons, and things like that. But halfway through going grade level up and up, we changed that to, instead of like little planets orbiting the center, it became like a cloud, a fuzzy cloud of possibility of where that electron could be. And to me, that's kind of like what qubits is saying. Until we observe it or measure it, like we said, it could be anywhere.
Right, let me restate that for the audience. So when you were growing up, you had the solar system model of like an atom, right? Electrons whirling around, and neutrons and whatever, and then or protons, and neutrons in the middle, and then, but then, as you were growing up, you found out, no, it's more like kind of a cloud of things, and these things could be in different places or not really any particular place until it's measured, and that's kind of the model. It's all about Heisenberg uncertainty, right? So how do we represent qubits? So we're done with bits now. We're going to stay with qubits. So there are really 3 main ways to represent qubits. One is you could represent it as in the Ket notation, which is a guy by the name of Paul Dirac created this notation basically to make it easy to work with vectors. Vectors are like one-dimensional arrays, kind of over on the right there, to the right of the Kets. And so they just represent vectors. So that 0 with the house on its side, that over there, that Ket, that represents the state of 1, 0, that vector. So that 1, 0, the first position is the off position, the second position in that vector is the on position. So in that case, it's saying this is off. This is a 0 state, It's all 0, 1, and then the weighting is 1. And then in the second one, the weighting here is on the 1 position. So it's all 1. It's completely on, completely off. So it's like a 0 or a 1. So that makes it really easy as you know, as classical developers, as we all are, to kind of think in terms of, okay, yeah, the ket 0, that's like a binary 0. That's a bit off. Okay, so then, but what about the superpositions? Okay, well, so now what we do is we kind of put something in front of it here, kind of a multiplier that says, well, instead of being all on or all off here, it's, in this case, the square root of 1/3 in the 0 state, and it's the square root of 2/3 in the 1 state. And so that's how we do it in ket notation, and this is how we do it in vector notation. Okay, again, this means 0, this means 1. Okay, you with me so far? Questions on that so far? This is really key. Okay, now there's another way of representing it, and unfortunately, it's an alternative way, but kind of a simpler way to get your head around to representing a qubit. So that's a qubit, that's a block sphere. Notice that the 0 is on the top and, you know, North Pole, 1 is on the South Pole, and then we have, you know, we have 3 degrees of freedom that we can represent stuff. This is the way that a lot of people, including myself, tend to draw the state of a qubit. And when teachers are teaching about it, professors are teaching about it, a lot of times it's easier to draw it this way. Now notice that, and to think about it this way. So notice that the 0 state is here, and the 1 state is there at the top. And so this is like, you know, very much just like a 2-dimensional graph, where you've got your x-axis and your y-axis. And so the way that we represent then, like for example, this superposition here, we represent it on a unit circle, which means we only, you know, the qubit representations are only on the circle itself, not inside, not outside. Unit circle meaning, and unit circle meaning that the radius is 1, okay? So here, this qubit is in a superposition of the root of 1/3 on the 0, and the root of 2/3 on the 1. And so that point is right there. And you'll notice because of the Pythagorean theorem, if it's a unit circle, that's always going to be 1. And therefore, the square of this plus the square root of this, see, the sum of the squares, right? So the sum of the squares equals, right? So anyway, 1/3 plus 2/3 equals 1, right? So, yes.
Question. On your original with the qubit, it's block sphere.
Yes.
So you showed it's spherical, so 3-dimensional. You got another degree of freedom. All of this is now been reduced down to basically planar. Is the 3rd dimension simply not used, or?
Okay. So the question is, you know, you've got 2 dimensions here. Why the extra dimension? What did we lose? Well, what we lost there, one of those dimensions is reserved for the complex plane. Like so, and thanks for referring to my next slide. So there's the complex numbers and imaginary numbers. You know, they get a bad rap, right, because of their names, really. I mean, why call numbers imaginary? If you think about it, well, negative numbers are kind of imaginary, right? You have negative 3 apples, right? So it's just a concept that we've kind of grown up with. Well, the same thing with imaginary numbers. And so imaginary numbers are quite simply, if you think of a number line, and you probably all know this, but you think of a number line, and then you've got real numbers, positive and negative, then you've got another axis for imaginary. And on the unit circle, imaginary, it's I plus, and then down here is negative I. And so you have this nice unit circle that has all of the complex numbers that we're going to use. And that, if you slice the block sphere in kind of horizontally, then that section is the complex plane. Okay. Now, so here, in here, so the amplitude of a complex number is pretty much the Pythagorean theorem as well, right? So because superpositions can be not only real numbers, but they can also be complex numbers, they have a magnitude as well. And so their magnitude is reflected. You just represent their magnitude, but you could represent any number of any superposition any number of ways, because you could do it in a number of ways with complex numbers. So, and thank you for the question. So here we have then, we know what these lengths are, right? And then the other thing about these numbers is, if you take the square of this number, which is here, right? So that's this number, the root of 1/3. You take the square of that, and that's the probability that when you observe this qubit, that it will be in that state. Same thing here. The square of this number, when you observe it, so the square of that number is 2/3, right? When you observe it, that's the probability that when you observe it, that it'll be in the 1 state. So nature does all these things, right? It allows you to store an infinite amount of information in a qubit, a pair of complex numbers, and then, as we'll see later, do all sorts of operations that bring in other qubits and do tensor products and could take all the atoms in the universe to store it. But then when you go to measure it, it collapses down to 1 or 0, right? So that's one of the tricks with quantum computing is to leverage nature, what nature's given you, but then and then set things up to where when you do measure it, that measuring is meaningful. Okay? Questions? Yes.
So, yes, I can understand this imaginary dimension. Right?
You can understand?
The dimension we're talking about here is imaginary, so. But I'm not sure that, then what about the state of the time? Because I guess I know that, what is the what is the unit of time? Can we expect this state of
coherence?
Yes.
Okay. So is that your question about coherence? Yeah. So the question is, with the underlying quantum computers and the fact that we're relying on very delicate states, very delicate quantum states, sometimes entangled, and how about coherence? Well, coherence is this idea that these qubits are in a state with particles or whatever underlying, kind of holding that state. But if it's very fragile, then how much time do you have to make these complex computations before you could decohere, and then everything just erases out from underneath you, right? So that's one of the challenges of building a quantum computer, is increasing your coherence times to lots of milliseconds maybe, or even a second or two, or whatever, through through cooling and superconducting and things like that. But then and so progress is being made there, and so it's just kind of a matter of time before coherence will be acceptable. So it is like IBM, for example. I think they've got a prototype 17 qubit computer, and its coherence time seems to be good enough to be able to run some simple algorithms on it, some simple circuits on it. Google's working on, I think, a 40 qubit, but in the next 3 years it'll be out. So that's a very good question. So let's see, complex numbers. So why do we need complex numbers anyway in a qubit? One of the natures, kind of the fundamental properties of quantum mechanics, is this wave nature. So if you think about light, like photons, then they have electromagnetic waves, and so we leverage those in quantum computing for their constructive and destructive interference. And so a very natural way to represent waves is with complex numbers. So on the horizontal plane in this unit circle, we've got the real axis, which we talked about, and then the vertical axis is the kind of the imaginary axis, plus going up, minus going down. And so in that, with a complex number, you can encode an amplitude and a phase. And so then by, as your complex number then varies, then it's defining a sine wave. And those sine waves, depending upon where they start, you could have two that are 180 degrees out of phase. And just like with waves in water, they destructively interfere with each other and make it as if there's no wave. Or you could have two waves that are of the same phase, and they constructively interfere. And so what that does with quantum algorithms is that you try to set things up to where the right answer constructively interferes, so that when you measure it, so the amplitudes go up for the right answer. So when you measure it, then the probability goes up that you're going to get the right answer. So that's kind of it in a nutshell, quantum computing in a nutshell. So now we'll move on to measurement. So here's a Dilbert cartoon. I'll let you read it yourself. But it's kind of the problem with measurement. So here's another screenshot from this really nice video, actually, from the PBS Infinite series on the mathematics of quantum computers. You use, when you're manipulating qubits, you're trying to set them up in states where they'll mean something through techniques like constructive and destructive interference. And so you're setting them up in those states through quantum gates. So you might have a state 0, 0. And so then you have a quantum gate, and then maybe the result of that quantum gate is this superposition of root of half 1, 0, 1, root of half 1, 0. Maybe another quantum gate puts it in this position. And so now when we try to observe it, we've got 3 different states it could be in, with probability half on this state, probability 1/6 in this state. Remember, we're taking the square root of the amplitude, or square of the amplitude. And then here, probability 1/3. So half plus a sixth plus a third, that should equal 1. And so when we measure it, then with those probabilities, we should see these values. And that's, I mean, it's kind of mind-blowing to me, by the way, that the way that the universe works can be reduced down. I mean, like, is like this, is like simple linear algebra and what's called two-norm probability, right? Where the two norms are two-norm probability where this and this equal 1. You know, the square of this and the square of that, take the square root of that equals 1. I mean, that kind of blows my mind, really, that it could be that simple. But that's the way nature seems to work. Questions? Yes.
On the screen before.
Yes.
Does that imply that there's 3 qubits? Or 1?
Okay, so the question is, on this screen, does it imply that there's 3 qubits or 1? Okay, so actually, you know, I a little secret here. I've paid different members of the audience like $5. I told them I'm going to pay them $5 for hinting at the next slide, and so you did it a little while ago, and you just did it, and I appreciate it. Thanks for being a plant in my audience. Yeah, this is. I'm going to explain this in just a little bit, but there's actually 2 qubits. So that ket notation there, the 0, 0, that represents a state that consists of 2 qubits. Okay, and that state is 0, 0, kind of like 2 bits. 0, 0 is 0, right? So, or you could also have 0, 1, 1, 0, 1, 1, right? So, here's 3 of the states of 2 qubits. The missing state is 0, 0. And the reason why it's not there is there's no probability. You know, when its amplitude was 0, so there was no reason to list it here because it's 0 probability when you measure it. It's gonna be seen. But this represents the first qubit. That's the second qubit. This is another combination, or another state, I should say. And it'll become clear on the next slide. Actually, that slide. So I wanted to show you a simple quantum circuit. So how do you program a quantum computer? Well, I mean, you could use a programming language, and there are some simulators that use a programming language. IBM Q's, IBM Quantum's computer, you can use a circuit, but then I also have a Python API you can use, and so you can use either one or both. But when you're first learning, I find it most effective to use a circuit because that's what's going on underneath. The name of this talk is Quantum Computing Exposed, and what I'm trying to do is kind of expose, pull back the curtains and show you what's going on underneath. And so what's going on underneath is that you have, or at least you can abstract it to a circuit in which over on the left, each one of those wires, each one of these 3 wires, and then over on the left you can see what's on the wire, is a qubit. And it starts in the initial state 0, there's a 0, there's a 0. So we have 3 qubits, and then we are using a gate. Actually, we're going to use the same gate on each one. It's called a Hadamard gate, and I'll explain that in a minute. But that puts it in a superposition, and then we do some sampling, and I'll show you that in a second. I'm going to take it to the live simulator. So in the presentation, all you do is you click on this link, and then it pulls up this really nice simulator that a person by the name of Craig Gidney, who now works for Google, created when he worked at Twisted Oak Studios. Is in my mind, he's very brilliant in the area of quantum computing. So this is a simulator that he built Here's some tools that you can use, some more tools down here. Here's the 3 wires. So our system has 3 qubits in it. Here's a gate. I just drug this gate from here, that Hadamard gate. And if you hover over it, it tells you what the gate does. So as a matrix, it says it transforms 0 into a superposition of root of 1/2, 0, and root of 1/2, 1. So basically what that is that if you have in that superposition, something in that superposition, then, and you measure it, it is equally likely that the cat is going to be dead or the cat's going to be alive. It's the same kind of thing with Schrodinger's cat, right? So it's equally likely that that qubit will be in a 1 state or a 0 state. So each of these then, it's equally likely that they'll be in a 0 state or 1 state. And so what's happening here is that it is sampling every half second or whatever, just like as if it were in like a real quantum computer, and you were then setting up the circuit and then sampling it. Okay, measuring every half second. What is the state of this qubit? Okay, it's off. What's the state of it now? What are the state of these 3 qubits? On, off, on. Okay, now what is it? Off, on, that type of thing. And so we're able to make a random number generator. Here we're generating random numbers between 0 and 7 using quantum mechanics. And then what this represents over here is the chance of being on if measured. Well, since the superposition of, I'll just go ahead and measure, I'll go ahead and bring an amplitude display down here. So here's yet another way. Here's a block sphere. We could look at the representation here. But here's another way to look at a representation of just 1 qubit. So this is a qubit, it's 0. And then the state 0 of this qubit is a value of 0.707, which is 1 over the square root of 2. And so if you multiply that, if you do the square of that, then the likelihood is 50%. And so the same thing with here, the amplitude of the 1 state of that qubit, it's the same. The value is 0.7, and the magnitude squared is 50%. Notice also in this display we have the real value up there, 0.7, and then we have the imaginary number, the imaginary component. And so if that imaginary number, for example, was 1 or something like that, then we would start seeing this arrow, this line go up into the imaginary plane, in imaginary positive or negative direction. So this circle is kind of the imaginary plane, as well as this real and imaginary plane. So that's the state of that qubit. As far as block sphere representation, it's representing it as well as half on, half off kind of thing, an equal superposition of being 1 or 0. Remember, with a block sphere, 1 is at the top, 0 is at the bottom, so here we are halfway on this axis. Okay? And then what we have over here, in answer to my colleague's question, is the composition of these three qubits. So when you have 3 qubits, let's say, then you have 2 to the n, 2 to the third states. So just like with bits, if I had 3 bits, I could have 0, 0, 0, 0, 0, 1, all the way up to 1, 1, 1. Got 8 states. With qubits, if I have 2 to the third qubits, which I would have 8 amplitudes. The amplitude of 0, 0, 0, do you see that tooltip up there where it says amplitude of 0, 0, 0? By the way, is this large enough to where you can see the tooltips, the writing in the tooltips? If not, please do come forward, or I can try to make things bigger. Please do let me know. Okay. So then here's the amplitude of 0, 0, 1, amplitude of 0, 1, 0, and also, you know, we've got the amplitudes, but when we also have magnitude squared, which, as we know now, is the probability or the percentage that, if measured, it's going to be in that state. So that's why we're getting a very equal but random selections of state here, because they're all, the probability is all 12.5% for every state. Okay? Now, this number over here, that's 0, 0, and then that little underline, then that you can fill that in like 0. This state right here is 0, 0, 0, or this state right here is 0, 0, 1. Okay, so those are the states. Okay, questions? Yes. Yes. Okay, so for the block sphere, is there a reason why it's pointing straight out rather than all the way to the right? So it's a matter of how it was rotated in the picture. So in this picture, the x-axis is pointing to the right for some reason. I guess so they could draw it better. You could see the line better. In this picture, the x-axis is pointing, you know, kind of straight out at us, and that's the way that this picture is kind of inaccurate as far as it's been kind of turned. The fact that you asked that question says that you're paying attention, though. So I may actually give you that fictitious $5 that I've been passing out. Okay. So that was a simple quantum circuit. Any more questions on that particular quantum circuit? Yes?
If you change that H gate to be an octave percent, that's possible in the simulator, would it change the outputs of the distributions?
If I change the what? If I change...
H gate on the left, you
Yeah.
said the 50-50 proposition.
Yes.
Can you change that to a 1/3, 2/3?
Well, by applying different gates, we could change different things, right? So, I mean, if I took it away, let's say if I took that 8 away, now, because of whatever state it's in here at the time, then it turns into then a combination of a quarter, you know, 0.25 probability, or 25%, that it'll be in 0, 0, 0, 0, 1, 0, etc. And that kind of makes sense, right? Because we've said that this least significant qubit is off. And so now the least significant qubit here in the combination is 0. Good question. Yes, question.
So what's an example of another gate? It was specifically named, so I'm assuming that implies that it's a 50-50?
So what's a example of some other gates? So you want $10? Is that what you're asking? Unbelievable, unbelievable, man. So there are some other gates. I'll get to them.
In the simulator, can you drag a nod in there and show us what it does? Or am I getting it further?
Yeah, I'm gonna do those things.
Okay, sorry.
No. I mean, when I told you to kind of, you know, point to slides up ahead, I didn't ask you to, you know, to point to all the slides up ahead. See, you're tracking with me. That's awesome. I appreciate it. So that's a simple quantum circuit. So now, if you started Quark out from scratch, this is what you would get. You would get an empty circuit. So for convenience, I put a link in there for an empty circuit. So there's nothing on there right now. And so I want to analyze that state real quick here. For what is that state? Well, we have 0 qubit, and the state is there's a 100% chance that it's 0, 0. And that makes sense, right? So the way that's, just to kind of show you different notations here, the way that's represented, remember we have 2 qubits, both in state 0, so that's represented as a ket. You could represent it as 0, 0. You could also represent it as two kets, 2 individual kets. And also you could put what's called a tensor product sign between them. Sometimes they do that. It's not very often. But each of these states, this state and this state, well, I'll just go with this. This first one is represented by that vector, right? It's fully the 0 qubit, right? Or fully in the 0 state. And this one's fully in that 0 state. And then we do a tensor product on that. And that's, the tensor product is explained in this really good article, which is actually some lecture notes by John Watrous from University of Calgary. But in a nutshell, you take the first vector or matrix or whatever, and then you'll multiply each. First of all, you're going to end up with n times m entries in the resultant vector, right? So, but anyway, we take this one, the 1, and we multiply it by 1, and that's going to be this first entry. Multiply this 1 by 0, that's the second entry. Multiply this 0 by 1, that's the third entry. Multiply the 0 by 0, that's the fourth entry. So what you're doing when you do a tensor product is you're taking a vector or a matrix, and you're taking each of the entries in the vector or matrix, and then kind of inserting or multiplying it, using it as a scalar to multiply by each of the entries of that matrix. So that's a tensor product. And the nice thing about the simulator is it kind of does that for you. So you have a couple of qubits over here, and we see over here then that it has kind of done the tensor product for us. So 1, 0, let's see, 1, 0, 0, 0, kind of like the tensor product that we saw over here, 1, 0, 0, 0. So to beat a dead horse then, we'll take another state, and that's this one, where, I don't know how that got there. It's supposed to be an X. That was weird. Okay, well anyway, I guess usually yeah, there's a little glitch happening there, but okay, so that's this state here where this is a NOT gate. It's also called a bit flip. And so that changed this 0 to a 1. And so now there's a 100% likelihood that that'll be measured as an individual qubit as a 1. And then this is still 0. And so then when you combine those and do the tensor product, then you get 0, 1, 0, 0, which is what we expect when we do that tensor product. Okay? So hopefully what I'm trying to do is give you some intuition between, because that was one of the hardest things for me in kind of getting up to speed when I was trying to get up to speed on quantum computing, which I'm still not, by the way. But is this idea of qubits and then tensor products, and how do those kind of map, and then trying to get an intuition for how I use gates then to influence the tensor product, the 2 to the n number of states, because this 2 to the n number of states, that's what's going to be measured, and then it collapses into whatever whatever the measurement was based upon the probabilities. So now we'll get to some quantum gates. So there's the X gate, which is the bit flip, and that's also called a NOT gate. It's called a poly X gate. The notation is X, and the matrix that you use. So there's something called a unitary matrix, and so all the gates that you use, all the quantum gates that you use, are unitary matrices. The reason why they're called unitary is they preserve the one norm, or the unit norm. So when you do something in the unitary matrix, then what ends up happening is, I've got a better picture of this, but I'll go back to this picture anyway. Is you're basically rotating the block sphere, or rotating this unit circle so that everything stays relative to each other, and so that you are preserving the one, the unit. The other thing a unitary matrix is good for is that it is reversible. So you could take a gate. I'll just go ahead and do it. Maybe drag we'll just take a simple case here. I'll put a Hadamard gate here, and then another Hadamard gate. And notice that the result is 0. And then notice on the block sphere it's 0. Because in this case, with the Hadamard gates, they are, by doing one twice, you're reversing it. Now, the reason why that is because the Hadamard gate is, it is kind of reflective there on this diagonal axis. So, like if you're familiar with the identity matrix, it's ones in the diagonal, from top left to bottom right, and then zeros everywhere else. So if you multiply by a matrix and it's symmetrical along that axis, then it's going to be reversible. It's going to be, it is its own inverse. So the way to prove that, by the way, just academically, is that if you take the square of it, if you take this matrix by itself, then it'll end up with the identity matrix. But all gates are reversible. So if it's not reversible by using it twice, it's reversible by using the inverse of that matrix. And so you can always, it's kind of cool about quantum computing, you can run through a series of gates and then run those gates backwards and then end up with the same state. And sometimes that's nice to be able to do that in a quantum operation. Yeah, kind of like a checksum. So then we have the poly Z gate. Now what that does is that changes the phase. So for example, in our simulator, and it changes the phase on the one state, on the one state of a qubit. So let's say if I set a qubit to 1 here, and then I apply a Z gate, you'll notice then that the phase changed. In this case, it changed by 180 degrees from over to the right to the left. So it changed from, remember the sine waves and all that? So you can use that technique when you're kind of setting up your quantum circuit. You can use that to have destructive interference, and I'll show you that in a minute. But it has no effect on a zero gate, on a qubit that's 0. Okay, just the one. And it tells you that here. It's the phase flip gate, negates phases when the qubit is on. Okay? Now the reason why we don't see that phase flip on the Bloch sphere is because we're in the one position, which is straight down, and so we can't see the Bloch sphere rotate. We can't see that rotate in the one position because it's already at the south pole. There's a little bit. Bloch sphere is supposed to give you all this more information, but it hides that from you, hides the phase from you, so it's not perfect either. Okay, questions? More leading questions. Who else wants to earn a fictitious $5 for pointing to my next slide? I'm sorry? You assume I'm going to start putting them together? Oh, right, yes. Yes, we're going to start doing that. We're going to start kind of building up some circuits. Okay. So then we have, let's see, we have a C0 gate. That's our first 2-qubit gate. It takes 2 inputs and then does this unitary transform, and then the result is, it's very simple. It's like it's a controlled NOT gate, and so if the bit is on, if the control bit is 1, then it flips the bottom bit. And some people kind of explain that or describe that as an XOR. It's very much like an XOR, exclusive OR. So I'll just demonstrate that. We've got we've got a state of 0, 0. I'm going to put a control bit here, and then so this is to make a C0, you just use the control bit and then you use a bit flip. So it's not doing anything here to the off, but if this is on, yeah, so to make it, what am I going to drag over there to make this bit on? What? An X. Yeah, okay. So if it's on, then it flips that off to on. But if this was on, then it's going to flip it to off. Okay? It's very simple, a C0. Okay, controlled NOT. Okay. Other questions? Okay, and then so that's you can think of those 4 gates. This isn't the only kind of universal set of gates, but it is a universal set of gates to where this, I believe, is all the gates that you would need to do any quantum algorithm. There are other sets of universal gates, just like with bits in classical bit logic. You can do anything with just only NAND gates, I think. Okay. If you need a refresher on matrices, because these unitary operations are matrices, then there's a refresher on how to do matrix. Basically, it's mostly matrix to vector multiplication. So this explains this kind of reiterates on the gates, and also gives you some intuition on what it does to this representation, this representation that we used. I want to go back and show you that it's the same one as this one over on the right. So I'm going to be showing you in this representation. These are drawings that one of the pioneers of quantum computing, Umesh Vazirani, he did a set of really good videos. One of those videos is single qubit gates, and I'd recommend that you watch it. But he went through and said, okay, the bit flip, there's the matrix, there's the symbol, and then this unit circle that represents a qubit. If you apply this, then what's happening is it's going to rotate about this axis, flipping 0, and 1. Okay, so that's how you can kind of visualize it in a unit, in the qubit circle. So the Hadamard transform, which this is the matrix for that gate. This is what happens, by the way. If you do a Hadamard transform on a 0, you end up with what's called the plus state. So this state that we've characterized as 1 over root 2 plus 1 over root 2, you know, with the 0 and the 1, that's also called the plus state. So it takes the 0 and turns into a plus state. Again, rotating on a slightly different axis here. You can kind of get an intuition about it there. And then also, it'll take the 1 state here and rotating along that axis, turning it into a negative state. That's a minus state. Minus state, in terms of kets, is 1 over root 2, 0, minus 1 over root 2, 1. The reason for the minus is because we're going a negative in the 1 direction, okay, to get down there. So that coordinate would be that. Okay. So this is like vector space, right? We're representing two-dimensional vector space. The basis for the vector, they call them in qubits, speak. They call them computational basis states here. One, you got the 0 and you got the 1, and then we're putting these qubits, representing them on the unit circle in vector space. Okay. So questions? Hadamard's a very useful transform. Yes.
I'm kind of curious, what does the hardware look like for these kind of circuits?
Oh, the hardware?
Yeah.
Okay, what does the hardware look like for these kind of circuits? So for like the underlying hardware for quantum computers themselves, yeah, I don't know. I really don't know. I mean, some of them are really cold. They're printed on like printed circuit boards and things I've seen, and that you'd have to look up that and just kind of see the different types, like trapped ion, like University of there's a university in England, I think it's Oxford, where they're building a trapped ion, so super quantum computer, so that you don't have to have superconducting. You don't have to take it down to almost absolute 0, but it's a lot different. You could Google it though. Thanks for the question. So you get $10 since I don't have a slide for that. All right, so then the Pauli Z gate, which is the phase flip gate, the intuition there is that you're rotating around this axis, so a 1 turns into a -1, a plus turns into a minus, but a 0 is left unchanged, and there's the matrix for it. Okay. All right, so now we're going to talk about more about measurement, and I'm going to give you a kind of a lab experiment that you can really relate to then and see. And in fact, I'll pass it around while I'm doing this, so that you can prove it to yourselves that it's true. Should have gotten it out before the presentation. You can cut this out on the tape, right? While I'm rifling through my bag. Okay. So what these are, I'm going to pass around. Do we need to take a 5-minute break? Do we need a 5? Okay. All right. So what I'm going to pass around then is some polarized lenses, and I'm going to give you 3 of them here. And what I'll do then is set up this experiment for you. and it's has to do with measurement. So the idea here is we have a polarized lens, and then here we're shooting a photon. So photons are oriented, they have an orientation. So the wave, the electric wave is oriented in some way. So it could be vertical, it could be horizontal, it could be a diagonal, whatever, but it has some type of orientation. So you can think of that orientation as a state. And so then, so here we have a photon that we're going to shoot into a polarized lens. Now this polarized lens has a vertical polarization. And so this photon that we shoot, it actually has kind of a diagonal orientation. So we're representing that diagonal orientation by this ket, with just a diagonal line, diagonal arrow. And we're saying, okay, if the polarization, the polarized lenses, filters, are vertical and horizontal, then those will be the basis states, kind of like the rest of the basis states we've been dealing with. And we'll represent this diagonally oriented photon as a superposition of the horizontal state and the vertical state. And we'll call that horizontal. So we could have, we would use a Hadamard gate, right, to get that. But so when we shoot that photon, then this lens measures it in the horizontal, vertical states. And it's going to collapse with probability half into one of those states. So some of the electrons will get through. If it collapses into the vertical state, it's going to get through. If it collapses into the horizontal state, it won't get through. Photons are discrete packets of energy. That's part, they're quanta. That's what quantum means, is discrete packets of energy. So a photon is a quanta. And so it's either going to pass this filter or it's not. And so it'll either collapse in the vertical and it'll get through, or it'll collapse in the horizontal and not get through. With me so far? Okay, so now we've got two lenses. And so this one in the back is vertically polarized. This one in the front is horizontally polarized. No light gets through, because if a photon being shot through the back lens collapsed to being vertically oriented, then its state is fully vertical, right? So there's no superposition that it would be, the orthogonal state is the one that we would wish it would take, and that's not possible. So it's completely dark, right? So that's represented here, where we have the blue line is the electromagnet, or the electric. So electric waves. The green ones are the electromagnetic waves. So that we're just thinking about the blue waves. So they shoot through, and then the ones that make it here aren't going to be able to get here. So 0% chance that we get out the other side. But now, if we interpose a lens at 45 degrees, we notice that it's not the case that even though we've introduced an additional thing in between them, it's not the case that it'll be darker. As a matter of fact, it couldn't be any darker, right? Because we are letting no light through. We're actually able to get some light through. And you can prove that with those things that I just passed around. And the reason for that is that here we've shot light through and it's collapsed to being vertical. And then here we're measuring in the plus state, in the diagonal state at 45 degrees. Well, it's either going to collapse to that state or to the orthogonal state. If it collapses to that state, then it's so there's a 50-50% chance it'll collapse to that state. And then now we've got another one that's oriented another 45 degrees, and we have that same thing. It can either collapse to that orientation or it won't get through. So either way, in each step, there's a 50% chance because of that 1 over root 2 superposition that it'll get through that additional filter. Now, is that nuts or what? But it's also cool that you can prove that with very simple polarized lenses for sunglasses if they're linearly polarized. So questions on that? Yes.
So I've seen this experiment before, but this is the first time I think the implication, which is it's only collapsed to that state while you're measuring. Right? So as you measure the first one, it's either vertical or horizontal. Once it goes through, it goes back to potentially superposition states. And now you're measuring again, so it's collapsing at that second filter. And some of them go through it.
That's close. That's close. Let me rather than repeat your assertion, I'm going to go ahead and just repeat it with what I believe to be the correct thing. Okay. So if light gets through here, and it's going to be vertically polarized. It gets here, and it's going to. There's a 50% chance that it will collapse to being polarized at 45 degrees, right? So if it makes it through, after this, it's actually polarized to 45 degrees. So it's not in some. It's in that state. It's in the. So let's call this, for lack of a better term, we'll call this the plus state. So it's fully in the plus state and not at all in the minus state, right? Those orthogonal states. So now, when it hits this one, again, there's a probability half that it will assume this state and go through, and probability half that it won't go through, right? So your assertion that the assertion I would color the assertion to say once it gets through this, it is in that 45 degree state. Okay. Make sense?
So the polarizing filter only blocks when it's perpendicular. If it's at a 45, it blocks 50%. So that's why, but it also, it sounds like it also, it's, what it's passing is 45, so that when that passes through the 90, getting back to where you had the three, yeah, that one.
This one?
You can kind of see visually when they're at 90, it's blocking everything. But if you put one at 45 between the two, you actually, you're changing what's being passed
Yes.
to that front.
Right.
To that front.
So each filter then, because it's in a superposition that's 50% probability that it's going to pass through the next one, you're actually going to pass through, 25% of the light rather than 0% of the light. What's interesting is then, let's say you change this, I won't get into this, but let's say you change that to 22.5 degrees. Then because of these, the amplitude formulas and things, then, going back all the way to here, the amplitude formulas, then what it works out to be is you're not gonna let 50% of the light through. You're gonna let 85% of the light through on the, and so it's quite shocking.
Yeah, but removing the central one, in the last slide that you showed, one further down, by removing the center one, it's either 0 or 90, meaning.
That's correct.
And so by removing the middle gate, you're saying it's binary. white, all open or all black.
That's
By
right.
putting that one in there, you're 50-50, and then the middle one is the radical, if you will.
Yeah, right. And the reason why that works is because it's collapsing to that state. And then, yeah. Yes, Matt. Not Matt. Oh, shoot, I forget your name. Is it Matt, right? Yeah, yeah. I know everybody's names.
We're observing that, yeah. What about the 45 degree enables the light to go from the 0 to the 90? Is it because of the drastic change of the lens that's it's allowing some of them to go through the first one, and those that get through the second one? Like,
So what it is about the 45 to 90 is that it's in a superposition in which there's probability half that because the 45 to 90 is a quarter turn, right? Or it's 45 degrees, yeah. And so that's like when we did this Hadamard transform, if I just put a Hadamard here, okay, so then the superposition is half probability that it'll go to this state and half probability that it'll go to that state if measured. And so it's a simple thing of when you changed it by 45 degrees, then that put it in a superposition to where, when measured, it's going to be equally measured as one or the other. So here, it's in a superposition of these are orthogonal 90 degrees, and then so this superposition is called the plus. But if because the square of these are 1/2 each, it's probability half that it'll end up in 0, half that it'll end up in 1. So it's the same thing. Okay. All right. So now we'll get on to the next one, and that is I know that what time do I need to wrap up pretty quickly, right? Yeah. Okay. All right. So I'm going to explain a classical algorithm in 2 minutes. Here we go. So this is called the Deutsch-Josse algorithm. And the idea, this is the circuit. So there could be one or more inputs there on like the 0 qubit. And then there's another one, which is an input like an answer bit. And the upshot here, I'll just explain the algorithm. The idea is that you have this oracle, this black box that you're putting inputs into, X number of bits into, and then the task is, by querying the oracle with sets of bits of your choice, you need to figure out, is that oracle, that black box, does it return a constant answer or a balanced answer? And so it's kind of a toy problem that was created to demonstrate that quantum circuits can do things much faster at certain problems. And so this is one problem. So the input, here are all the inputs for the 8 values. And if it's a constant function, if it's constant black box, it's always going to return, let's say, 0 or 1. But let's say that we do 0. If it's a balance, then one way of doing a balance would be, if it's even, return 0. If it's odd, return 1. So classically, how many invocations would we need? Well, if we had 8 states, 8 possible inputs, we would need 5, because 4 invocations maybe we're unlucky and those 4 could return all zeros, right? So maybe we do this one, this one, this one, this one, and it's all zeros. So we need that 5th one to prove whether it's balanced or constant. Well, how many do we need in a quantum algorithm? We just need 1, right? And so you've got this exponential speed up. Check me, is that exponential? Computer science, PhD, that's an exponential speed up, right? Okay. All right, so the idea then for this algorithm is we create a superposition of inputs to the oracle, and then we use something called a phase kickback for constructive, destructive interference, and that's explained here, but here's the circuits, and then I'm going to go ahead and just run this in the quantum simulator. And so here's the superposition with Hadamard gates. We have this black box, and this one is going to return constants. And we have an answer bit here that we prime with in a 1 state. And then notice with constant that here before we measure, here we're measuring over here, but here before we measure, before we do a Hadamard to expose the answer, we notice that we've been able to finagle things to where we're making it so that it's constructive interference. So by doing that, by taking this state and then doing the Hadamards on it, we're coming up with an amplitude of 0, 0, 0 of 1, which is the 0, 0, 0 state, which says, in our algorithm, in our circuit, we're saying if we come up with that, it's constant. But now, if I replace this, and I've created a balance gate over here, then we see that we've set up destructive interference. And when we do Hadamards on that, then we end up with something other than the 0, 0, 0 state. And so I know we need to stop, but that's kind of it in a nutshell. When you're creating quantum algorithms, you set things up to where the probability shows you what the answer is. And so with this particular algorithm, it just takes 1 invocation. So I'll take any further questions, and I know we need to wrap up. Other questions? Yes?
One of the first things you mentioned was the possibility of doing secure communications by taking 2 entangled photons, firing one off to a satellite, and then basically changing one, and the other one changes, so you can now communicate information.
Yes. So here's, by the way, here's in the Quark simulator, it's got there's a menu option called quantum teleportation, and so here's just a counting thing that's making it it's making the input step up and vary, right? And so there's a block sphere that represents the qubit, and then there's some gates and doing some measurement according to the quantum teleportation circuit, one of the circuits that they use. And then here is the teleported qubit. So it's not actually, it's the same state. And there's something, and I'll end with this. So there's something called the no cloning theorem, and that's one of the reasons why working with qubits is secure, is because it is not possible to clone a qubit. You can teleport it, so you've got an entangled state and you're able to make this state appear over here, but you can't clone it. So, if you tried to measure this, then it would collapse, and so you can't actually make 2 of the same qubit. So anyway, I need to let you go. Thank you very much. You've absorbed a lot, by the way. You've done very well. Thank you.